going to make sure that I've got some sound here. It appears I am recording. Video's working. Okay. All right. Well, this is going to serve as our live content. Oh, I have my microphone plugged in. Make it sound even better. Okay. I want to make sure that I am recording and that the sound is working. Well, I guess I'm just going to have to go for it. I want to make sure, let's see, microphone, camera. Never done this before, so we'll see how it goes. All right. So our content for last week and this week, our focus is priority number one, what is seawater like? Because we know fresh water, right, is water without salt in it. Ocean water, we know one thing, it's got salt in it, okay? There are a lot of other things that are dissolved in ocean water, of course, because everything that water touches, it dissolves a little bit of. So every time rain falls on a mountain, it takes a little bit of those minerals and it rolls them off into the ocean. So the ocean is made up of minerals from the land, as well as minerals that are dissolved from the ocean floor. And then also we've got a lot of living things, both living in the water, dying in the water, and then decomposing in the water, right? So there's this massive constant cycling of nutrients, salt, and then, of course, we got temperature. Because we know that hot water or warm water doesn't act the same as cool water. So all of these things are going to come into play when we're talking about the ocean. But the things I want you to remember mostly, okay, number one, water acts the same as we've talked about all year, right? So warm water rises, cool water sinks. That's a really important piece of information to know for oceans. When we get to currents, that'll be even more important. But for right now, that's number one. Water still acts the same way in the ocean as it did on land or as it does in a pot on your stove. And then the other thing is that because the ocean is so large and because there's so much water that covers the face of the planet, it is a dynamic system, just like the atmosphere, meaning that it never stays exactly the same from minute to minute in any one place, right? So anywhere on the globe, any spot in the ocean is always changing in temperature. Sometimes it changes a lot, sometimes it changes just a little bit. It's always changing in salinity. Sometimes it changes just a little bit, sometimes it changes a lot, okay? So there are always these, like I use this word dynamic a lot because it's meant to refer to this constant changing of the ocean, but there are things that stay constant, like the ocean is salty, okay? The ocean has temperature differences. The ocean covers 71 to 75% of the globe, depending on how you look at it. I call it 71, but that's just me. All right, so let's get to talking about some of these characteristics of the ocean and the planet that we're used to. So here's a good example. Is I want you to just look at this. Okay? Do you see a ton of land, or do you see primarily water? Hopefully, if you're looking at this map the way I am, you see primarily water covering the globe. And this is a great example. Looking at it from the North Pole and the South Pole, you can see just how much of the proportion-wise is covered by the planet. Of the planet is covered by the ocean. So 71% of the Earth's surface is covered by water. That includes rivers, lakes, oceans, and all water. We have four main oceans. I'm going to take the video preview off because I'm afraid that might be blocking some of what we've got here. We've got the Arctic Ocean, which accounts for approximately 4%. Indian Ocean, 20%, slightly larger. Atlantic Ocean, getting bigger at 28%. And then the Pacific Ocean, which you guys know is the largest, is our 48%. So the Pacific Ocean accounts for almost half of all the ocean on the planet. And this is where we get to the part where it is really hard to imagine, okay? I have sent out a couple of different videos so far, and I'll send out a few more because the ocean is a little bit tricky to wrap your head around. It's way bigger and way deeper than your mind kind of accepts. And there is a lot more of the ocean unexplored than there is explored. So here's where I want to throw a couple of figures at. Okay? Figure number one. Out of all the places on Earth that living things can exist, so anywhere that life can live, 99% of that space that's livable is in the ocean. Approximately 1% is on land. So think about that, all right? That puts the ocean in a position where it contains the most livable space on the planet by far. So, and then the last part is that we have only discovered or laid eyes on or measured about 3% of the ocean. Okay, so let that sink in for a second. So 97% of the ocean, generally ocean surface, ocean bottom, has never been seen by a man, a human, or a recording device. So just imagine what that opens up for possibilities. I mean, that almost means that there has to be an organism out there in the ocean we haven't discovered yet. It almost requires that. Now, it wouldn't be an organism living at the surface of the ocean, because we got boats everywhere and we got fishing going on at the surface everywhere. It would be something that lives probably deeper. So anyway, those are some figures I wanted to throw out to you just to get your imagination rolling, because this stuff really is pretty amazing. But let's get back to what water actually is and how it got to be. Okay, so the first thought, we talked about this a little bit before, is where did the oceans come from? Before we got cut off last week, this is where we started to talk about. First thought is that when Earth first formed, we had a lot more volcanoes at the time. Okay, generally, magma coming out of the Earth's surface, aka volcanic activity, was at a very high level early in the Earth's history, and this would have exposed a lot of gas and a lot of water vapor into the atmosphere. If enough water vapor gets in the atmosphere, that water vapor will form clouds. And if you have clouds, then you will get rain. Now, if you see this as a progress, like here's the step system, is if you start with a ton of volcanoes, you get a ton of clouds, and then you get a ton of rain. And we're talking rain for thousands of years. So this was our first, how the oceans came to be. Second thought, and this is where I combined in what happened from off the planet, was that actually comets and some asteroids contain a lot of water. And we know that early on in the Earth's history, we were bombarded by a lot of pieces from outer atmosphere. From the solar system. So if enough of these things impacted the Earth, they would leave the ice would melt and turn into water, contributing to the world's oceans. So those are the two thoughts as far as how we think we got it. Now, aside from that, and this is, I know I've said this already, but we're getting to what is inside ocean water. All right, so ocean water, as I said before, has lots of stuff dissolved in it. Number one, sodium chloride, salt. Sodium chloride. So if you put sodium and chlorine in the right proportions, you get table salt, essentially, right? So the stuff that you use on your food is sodium chloride. It just happens to have been, purified so that there's nothing else there except for sodium chloride. As you can see from this pie chart, we've got a lot more things dissolved in the water than just sodium and chlorine. We've got sulfates, magnesium, calcium, potassium, trace elements, bicarbonates, which are usually from living things. And this is the stuff that's floating in seawater. This is the stuff that is dissolved. So keep that word in mind, dissolved, right? That doesn't mean that it's mixed in and floating in the water. That means that it's actually chemically mixed into the water itself. It's been dissolved, so unless you pull some fancy maneuvers, you're not going to get it back out. And then also waters and acid are added to the ocean because, as I said before, when water falls on rock, it takes a little piece of that rock with it, whether it be a chemical reaction or a physical reaction. And those are carried into the sea, so we get lots of acids and lots of minerals in our ocean because of runoff. Very cool. All right, so here's a couple of factors, a couple of numbers to throw at you. All right, so if I say that the average salinity of the ocean is 35%, okay, that's not correct. See how this is not percent up here? This right here is 0/00, clearly not a percent signal. That is a parts per thousand signal. Okay, symbol, sorry, not signal. So the average salinity of the ocean is 35 parts per 1,000. That means that every 1,000 parts seawater, you take 1,000 liters or 1,000 gallons, you're going to find that 35 parts of that 1,000 are salt. Okay. And then we get salinity that, if you think about this hard enough, it makes tons of sense. If there's a lot of fresh water going into the ocean, like at the mouth of a river or where a glacier meets the ocean, you're going to have much lower salinity, right? You'll have much less salt in the water because you have lots of fresh water. And the opposite is true for where there is, if the sun is strong or if the water is not being fed by fresh water, evaporation happens faster than precipitation and you get very high salinity. So good examples of this would be like the Dead Sea. The Dead Sea is such high salinity that you can float in it without having to do anything fancy. You just lay back and you float. So there are parts of the ocean that have much higher salinity because the sun, like for instance, near the equator, higher salinity because the sun is basically always shining on it, okay? And if the sun is always shining on the ocean, then that's going to evaporate the fresh water and leave the salt behind. So the water that's left behind gets saltier and saltier. So a way you could think about this is a gradient. Up at the poles, there's a lot of ice, and that means that there's fresh water being deposited into the ocean, right? So the poles, you're going to have more fresh water, less salt. At the equator, because there's a lot more evaporation happening, you're going to have more salt, less fresh water. Okay. That's important. So some of the natural processes that I just described that affect salinity are things like icebergs falling into the ocean, sea ice, because that traps a bunch of fresh water, but the sea ice doesn't trap salt, does it? When ice forms, it pushes out the salt molecules. So you will have salt molecules in the water. So the more sea ice you have, the more it'll affect salinity. Other things like runoff and evaporation. And typically evaporation happens, near the equator, okay? Runoff here, we've got pointing to the Mississippi River Delta. Icebergs up here in Alaska, and then, of course, a good portion of the Arctic is just covered with sea ice. It's not locked up. It's just floating ice. Okay. And all right, so there are 3 temperature zones of the ocean. So that's what I just covered was salinity. Let's talk about temperature. Temperature starts with the surface level where you've got a relatively warm temperature, right? Because it's in the sun, it's near the air. The air is pretty warm comparatively. So it makes a ton of sense that the surface would be the warmest place, right? And especially where the sun penetrates. If the sun is shining on anything in the water, that thing is going to warm up, right? So that means the surface zone is going to be the warmest. Next one is thermocline. We call this a thermocline because it's not the same temperature. It's a changing temperature. A cline means like an incline or a decline means a change, right? An incline means change in altitude. A decline also means a change in altitude, right? Similar to like acceleration and deceleration, they're kind of opposites. So anyway, so a thermocline means a temperature difference. So the thermocline refers to the place where the temperature is changing. The surface zone actually stays pretty regular up down to about 200 meters. Then it starts to change, and you've got your thermocline. And then down here, 1,000 meters and below, it stays pretty cold. Like the temperature is not going to change drastically from 1,000 meters to 1,200 meters. It won't happen. The temperature change from 400 meters to 600 meters is pretty dramatic. Temperature decreases with depth. Okay, so the farther down you go, and this is a good example because you see how it's light blue at the top and dark blue at the bottom. Where there is light, there is more warmth. Where there is no light, there is less warmth. So that makes sense if we think about it gets colder as you go down to the bottom of the ocean. All right, and the bottom of the ocean is considered from 700 meters down. That's deep water. Now, how this will come back to us, and I want to present this now before we go over it next class. But surface and deep water, they do not act the same. All right? Deep water acts like deep water. Surface acts like surface water. And the thermocline is where they mix. Think about that. Warm water on top, cold water on the bottom. This temperature change is happening because the warm water is mixing with the cold water inside the thermocline layer. Okay. Outside the thermocline layer, you've got some pretty steady water. Like it's pretty cold, pretty consistent, and pretty, like it's high. Oops, sorry. Go back, please. Oh, wow. Well, let me go back. All right, well, anyway. The pressure at the bottom is high, pressure at the top is low, and so you can see these trends happen a lot. All right, let's talk a little bit about the ocean floor because this is included in the ocean and what it's like. The ocean floor, of course, guys, is huge. We learned a lot about it when we learned about seafloor spreading and continental drift, and we learned about trenches. These are all features on the seafloor that basically they do things like they dictate what kind of life can live there. They dictate what kind of land features you'll have on the bottom of the ocean, because they're typically not land features, but you get the idea. Like there are mountains on the ocean floor, there are plains, there are plateaus, there are all sorts of things down there. So we call the edge of a continent that is underwater, we call that the continental margin, right? Just like the margin in a book or margin in a page, it's where one section separates from the other section. It's where the continent separates from the ocean. Okay, so the different regions, let me move. Here goes my puppet. So the different regions are broken up into these pieces, and these are the typical terms that you will see on your SOL. So starting from the continent going out, we've got continental shelf. This is where we do a lot of fishing. This is where we do a lot of swimming. This is where we do a lot of boating, okay? Once you go past the continental shelf and near the continental slope, you can do some deep water fishing out here. There's lots of fish out here that live here. But once you go further out, you're talking about a really deep ocean. So a couple things you'll see on the seafloor map. Mid-ocean ridges, where the ocean floor is being created. Sea mounts, which is literally just a mountain underwater. Got a mountain underwater, you don't call it a mountain, call it a seamount. Seamounts, if they break the surface of the water, they'll become an island. This is how we got Hawaii. This is how we got many other islands in the Pacific, is that we had a volcano, underwater volcano, that built and built and built and built up until it broke the surface of the water, and it becomes an island. It's fun. And then, of course, we got two new terms here. Well, three, really. Continental shelf, continental slope, and then we've got abyssal plain. That's one of our new ones, because abyssal plain refers to the flat part of the bottom of the ocean. The flat part, when it says plain, it means flat part, of course. Abyss means the very lowest you can go. So our shelf extends outward all the way to what we call the shelf break, okay? And that's where the edge just falls right off. Shelf break is where it literally falls off. Now, you guys have seen something like this. If you've been to the beach, there's a part, like if you've been to a beach where there's sand and there are waves, usually if you walk out, you'll walk out in sand for a bit, and then eventually there's a little drop off. Now, that's not the continental slope, but it's similar to it on a much smaller scale. There's usually like a sand drop off, because what the waves do is the waves bring up sand, deposit it right at the beach, and then when they roll back, they drop it, it only goes back further out of the ocean and gets dropped. So that usually at most beaches, you'll have like a sand shelf that you walk out and the sand gets softer and softer until it's like, maybe it's hard bottom. And that's because of wave action, but it's really similar to how the continental shelf goes out, 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 out flat and then drops off. Okay. And then of course you guys know that the trench is where this continental plate ends and another plate begins. The seafloor begins at the trench, right? Well, seafloor technically ends at the trench because it's subducting. And that's where your continent begins. Okay, what else have we got here? Next one is your slope, which we call, like if you've been skiing, you know that you need a downhill or uphill to slope. And then we'll talk about rise when we talk about a different type of coast. We've got passive and active coasts. Now, if you want to think about it this way, an active coast, active coastline or active shelf is where you have a trench where some seafloor is being destroyed and your continent is meeting with that other plate. Passive ones do not have a trench. So two types of margins, and I think this is where we're going to leave it for today because we're going to get into currents and ocean life in our next two sessions. But the two types of margins, okay, mainly, and this one you can see is continental margin. The continental margin includes from the very first drop of water, you want to call it high tide line, where the water meets the shore, all the way out past the break, past the slope, out to the abyssal plain. That's your continental margin because it includes all the way from where it's still continent, all the way out to where it is total ocean. So continental margin includes from the dry land out to where the ocean is deep. So it includes all of these features, both the continental shelf, the continental slope, out to the abyssal plain. Okay, and that's where your continental margin stops, and it becomes ocean. So up to this point, we're talking still continent, up to the outer margin marker. And of course, you guys can see there's a few different features in here, like a deep sea fan, alluvial fan. We got submarine canyons in here. We've got a big canyon right off the coast of Virginia. This is not too dissimilar from the east coast of the United States right here. It's actually very similar. This would be like a North Carolina, Virginia type area where you've got a long shelf where the water's warm. It's great for swimming and fishing and all sorts of stuff. But then there is a shelf break where the canyon drops out, and you get a bunch of different animals that live in a canyon. So if you've ever been to the Virginia Marine Science Center and Aquarium, you have seen the tanks that they've got there that are dedicated to the canyon, the ocean canyon. I think that's what, they've got a couple different tanks there, and one of them's called a canyon. So there are two different categories. One is passive. This is the one I referred to as not having a trench. This is what we see on our side of the United States. Passive. It's correct. Okay, so that means the continental margin is really wide. The space that goes from dry land out to the open ocean, long. Okay, big. Not near any plate boundaries. These are passive. There's no plate action going on here. Okay. The other one is an active one. This is the Pacific Ocean coast. Now, in the Pacific Ocean, what you see is you don't see the same kind of long shelf and then drop off. What you see is a shorter shelf and like a crazy drop off into a trench. So if you see what I'm seeing here, on the west coast of the United States, we've got mountains. Okay, so we've got a big continental crust right here. And that big continental crust is being subducted by the oceanic lithosphere, aka seafloor, right? And where that happens, we always get a trench. So if you can imagine our coast on the east coast of the United States, you can walk out for quite a bit. And you can take a boat out for quite a bit and put your anchor out. This has a situation where the continental margin between where the land ends and the open ocean begins much narrower. Okay, so wide continental margin on the east coast of the United States, narrow one on the west coast. Active continental margins tend to be narrow, thin, and passive ones tend to be very wide. This is the point I'd say any questions, but you can't ask any questions right now. So this would be our Pacific Ocean. These would be like our Cascade Mountains in northwest United States, because they are like Mount St. Helens would be the one that's erupting right here. Yeah. All right. Oh, and I just said that. At a passive continental one, you will not see a trench. You will not see a trench. But if you're looking at an active margin, you will see a trench.